Coming to the second example of non-dimensionalization and visualization, let's consider this problem. You may have seen this problem before from your course in mechanics, but if not, doesn't matter. It's a simple enough problem to solve, and we will take up this example in our as our next problem. So let's consider a hill, and on top of the hill, let's say there's a man standing on top of the hill. The man holds a ball and he throws a ball at some angle theta. The hill makes the angle phi with the horizontal. So hill has a slope, the slope makes an angle phi with the horizontal. Man throws a ball makes a parabolic trajectory, and it falls down and hits somewhere on the hill slope downwards. The problem is to find out what is the distance, what is the horizontal distance from the man's position, that is right underneath the hilltop, all the way to the point where the ball hit the slope. So in order to solve this problem, first we need to do is define the problem, that is lay out the coordinate system, write down the basic physics components, then we will translate it, we will take the equations that we have obtained from physics considerations, we will translate them into non-dimensional form, so that we can take, then they become mathematical equations without any dimensions in them, and we will analyze those mathematical equations, visualize them, and we will learn something about the solution from our visual results. Okay, excellent. So laying down the coordinate system, we need to first lay down the origin. So my second picture over here shows the origin. Let's take the origin right underneath the man at the bottom of the hill. This dotted line shows the level of the ground. This is the line of the horizontal. Hill makes the angle phi with the horizontal. We throw the ball at the angle theta. We'll ignore the height of the man compared to the height of the hill. Let's assume hill is much taller than the person. As the man throws the ball, it may so happen that the ball lands up somewhere away from the hill, and then there is no solution. So we have to find out the condition for which we will get a solution. That means the ball, we have to find out the relationship between the angle theta, phi, h, so that the ball hits somewhere down the hill. So to do that, first we start with some of the known facts, that the trajectory of the ball is going to be parabolic because it's a constant acceleration along the negative y direction. The acceleration due to gravity is constant, so this is a constant acceleration problem. For constant acceleration problems, the trajectory is always a parabola, so we will take that trajectory as a parabola, and we will establish that y ball, that is the trajectory, the y coordinate of the ball is given by ax square plus bx plus c, where a, b, c are some constants. So this is the equation of the trajectory of the ball. Y ball as a function of x is ax square plus bx plus c. Now this trajectory intersects somewhere with the hill, so we will also look at the equation of the slope of the hill. The equation of the slope of the hill is represented by a straight line, and then we will take y hill, that is the height of the hill, as a function of the x coordinate on this side of the hill as alpha x plus beta, where alpha is the slope and beta is some constant that we need to figure out. So these are the two equations. This is the equation of the trajectory, and this is the equation of the slope. Now I have to find out for what values of x these two curves will intersect with each other. Of course, we already know one solution, that is when the ball is right on top of the hill, which corresponds to y equal to h and x equal to 0. So when y is equal to h and x is equal to 0, the ball is placed at the top of the hill, and that is a point of intersection for the slope of the hill and the trajectory of the ball. The next point of intersection is what we need to find out, which is this one, and this may sometimes exist or may not exist depending on the various parameters of the problem, that is the height of the ball, the velocity of the ball, the angle theta and the angle phi. Now in order to find out these coefficient a, b, c, alpha and beta, we will find out the physics constraints that we already know about this problem, and we will use those physics constraints to find out the coefficients a, b, c, alpha and beta. That brings us to translate stage. We want to translate this into a mathematics problem. So let's add a few more physics inputs. Here I have taken 5 conditions because I have got 5 constants a, b, c, alpha and beta. So here I have taken 5 different conditions. First one is position of the ball. I know that y ball at x equal to 0 is h. So that is one condition. I also know that when I throw the ball at the top of the hill, dy ball by dt at x equal to 0 is v sin theta, because I know the angle theta. I also know that d square y ball by dt square, that is the acceleration of the ball in the y direction, is minus g, which is always minus g independent of what the position is. And for the hill, I know the top of the hill is y hill 0 equal to h, and the hill angle is dy hill by dx is equal to minus tangent phi. So top of the hill at x equal to 0, we have top of the hill, so that is why y hill is equal to h, and dy by dx, that is the slope of the hill, is equal to minus tangent of phi. Okay, so we'll take these 5 pieces of information and use them to determine a, b, c, alpha and beta. Let's go ahead and solve this with the paper and pen. If you want to solve it yourself and take a pause, go ahead, do that. Alright, so our equations were y ball is equal to ax square plus bx plus c, and y hill equal to alpha x plus beta, using the condition that y hill at x equal to 0 is h, and dy by dy hill by dx at dy by dx is minus tangent phi. We can go ahead and fix alpha and beta first. Using this, we can calculate dy hill by dx, and that is just alpha, which must be equal to minus tangent of phi. From this condition, we get y hill equal to h, that means beta is equal to h. So therefore y hill is equal to minus tangent of phi times x plus h. So that's the equation for y hill. I want to use other pieces of information, the other 3 conditions, to find out a, b and c. Okay, let's go ahead and solve for the second equation. Equation of y ball as a function of x is ax square plus bx plus c. My 3 conditions are y ball at x equal to 0 is h. This implies that c is equal to h. I take the second condition, which says that dy by dt, or dy ball by dt at x equal to 0 is equal to v sin theta. We evaluate the left hand side, dy by dt, we get 2a x times x dot plus b x dot plus c equals v sin theta. We substitute x equal to 0, and that gives rid of this term, and over here we substitute x dot equal to v cos theta, which is the velocity of the ball, or horizontal direction of the velocity of the horizontal component of the velocity of the ball at x equal to 0. Therefore, we get from here b v cosine theta plus c, value of c is h, is equal to v sin theta. Oh, sorry, there's a mistake here. I should have, when I take dx by dt, there is no c, so we get rid of that, we get rid of that, and so we just have bv cosine theta is equal to v sin theta, and that gives me b equal to tangent theta. At this point you can verify that b equal to tan theta is dimensionless, y has dimensions of length, x has dimensions of length, so b should be dimensionless, and that's what we find. Similarly, c has dimensions of length, and we find c equal to h, which has dimensions of length. So these are some of the cross checks we can make while during the calculation. Now using the third condition, which says dy by dt square is equal to minus g at all axes, but definitely at x equal to 0. So we can calculate dy by dt of the ball. We already have calculated dy by dt as 2ax x dot plus bx. Taking another derivative of that, we get 2a x dot square plus 2ax x double dot plus bx double dot equal to minus g. Evaluating the left hand side at x equal to 0 simplifies a few things. First of all, this term vanishes. Then also, because x double dot is always 0, there is no acceleration in the x double dot, this term is 0, and I am left with a equal to minus g divided by 2a x dot square evaluated at x equal to 0. X dot at that time is v cosine theta, so I get 2v I get minus g by 2 v square cosine square theta. Okay, so putting it all together, we have got minus g by 2v square cosine square theta plus bx, which is tan theta x plus h. Okay, so let's go ahead and now look at those two equations. Putting these conditions, I found that y ball is minus g by 2v square cosine square theta x square plus tan theta plus h. Similarly, for y hill I have got minus tan phi x plus h. Now these two are equations which contains dimensions in them. The next thing I want to do is I want to non-dimensionalize these equations. In order to non-dimensionalize these equations, I want to put out the dimensions of all the quantities. So y is measured in dimensions of length, x is measured in dimensions of length, and both of them I can non-dimensionalize by a natural dimension of length that is present in the problem, which is simply h. I can measure both x and y in units of h, which means using all of that, I can go ahead and divide y ball of x by h, and when I do that, there should be x square here. When I do that, I get minus g by 2v square cosine square theta x square by h plus tangent theta x by h plus 1. Now it's interesting to note that this term is dimensionless, this term is dimensionless, and this term is dimensionless. So this term should also be dimensionless, but I want to represent x also in terms of h. So what I will do is Because I've got x square here, I'll make this h square and multiplying a h over here. Now given that this term is dimensionless, x by h is dimensionless, I also conclude that this must be dimensionless. In fact, dimensions of v square and gh are same, so indeed this is dimensionless. What I'll do now is I'll define capital Y or block Y as Y ball as little y ball over h and capital X as little x over h. In terms of these, my equation simply becomes y ball equal to this constant which I am going to define as gamma so I get gamma x square plus or minus gamma x square plus tangent theta, which is already dimensionless, times x plus 1. So that is my non-dimensionalized equation for the trajectory of the ball, and similarly I can non-dimensionalize the equation for hill. So I'll define y hill as y hill divided by h, then I simply get y hill equal to minus tangent phi times x plus 1. Sorry, I should make one correction. I did not define gamma, sorry. So I should define gamma here. This is gamma x, and gamma is a dimensionless constant, so I'll define gamma as gh by twice v square. Then we'll have a cosine square theta here. Theta is a different parameter, so I want to keep theta as a separate parameter. I don't want to absorb theta inside gamma. Gamma is just a measurement of h over v. G is the universal constant, h is the height of the hill and v is the speed with which we throw the ball, and gh over v square is a dimensionless quantity. So v is a measure of the speed with which we throw the ball, or the inverse square of the velocity of the ball. So I have got 3 parameters in this problem. The 3 parameters that I have in this problem are tangent phi, gamma and theta. So phi, theta and gamma are 3 of the constants that are given to the problem, and depending on what the values of these 3 constants are, my solutions can change. So let's go ahead and analyze that. Here's my final equation for y ball and here's my equation for y hill. And now, since because these are 2 abstract equations without any dimensions, y is dimensionless, x is dimensionless, gamma, theta and phi are parameters, I can go ahead and plot this by using the plot command like this. So I make a plot for this equation for y ball and for y hill and the ground level, which is y equal to 0, that is the x axis, and I choose some values of the parameters phi and theta. I set phi equal to pi by 6 and theta equal to pi by 3, and I set gamma equal to 1. Remember that always the dimensionless parameters of the problem, once you non-dimensionalize, are always order 1 quantities. So you will always tend to pick some order 1 numbers for these quantities. That is why I said gamma equal to 1. 2 small values of gamma or 2 large values of gamma will end up giving you unphysical situations. If I plot all of these 3 things with these values of theta, phi and gamma, I get these 3 curves, and for this particular case, these 3 choices, I do get a solution. If I change gamma, you see that I may end up getting no solution, and gamma equal to 10 becomes very large. So at some point gamma equal to 3 corresponds to a situation like this. Now, it may appear to you that the angle of the hill is changing, but really it's the relative value of these parameters that is changing, and it appears in the plot that you are changing the value of the hill, but we have kept the value of the hill, angle of the hill as constant, and we are changing gamma, which is essentially changing the speed of the ball. So gamma equal large value of gamma means small value of the speed or a large value of the height of the hill, and that shows you how the solution changes as you increase gamma. Now we can actually go ahead and analyze this by manipulate command by manipulating all three parameters and find out when do we have a solution and when we do not have a solution. In order to manipulate this, watch the lecture on how to use the manipulate command and go ahead and make a plot of these three functions: y of the ball, y of the hill, and the ground level. When I make a plot, do a manipulate of all three of them, I have set some ranges of the parameters for phi, theta, and gamma over here. For example, gamma I have set from half to 2, and I have taken the canonical value as 1. I can go ahead and move the sliders now, and you can see what happens when I move the slider. As I move gamma, the velocity of the ball changes, and as a consequence, the trajectory of the ball changes, and you can see how the solution, that is where the ball falls on the hill, changes. Let me go ahead and change theta now. As I change theta, again I am changing the angle at which I throw the ball, and that also changes the trajectory. Let me go ahead and change phi now. As I change phi, I change the angle of the hill, and as you see, if the hill becomes more steep, we lose a solution. If I change theta, you see that doesn't really affect the solution. For if theta goes to 0, I throw the ball horizontally, I have a solution, and as I increase theta, that is my throw is more and more vertical, I still have a solution, given that the hill is not too steep. For a steep hill, again, a horizontal throw will probably not lead to a solution, and you'll have to probably end up throwing it vertically. Similarly, gamma affects the speed of the ball and changes the trajectory. So if gamma is very small, then also you'll end up having a solution, and ball will end up going very far away. So this simple example shows how the interplay of various parameters in the problem can affect the solution. Now we can actually go ahead and find the condition. When do we critically have a solution? That is, when do we have a situation like this, that the ground, the hill, and the ball all meet at the same point? A situation like this is the critical solution. You slightly deviate away from this critical condition and you lose a solution.